Welcome to all for the minimal spanning tree. Now you find the minimal spanning tree by implementing the algorithm. So for this, find a minimal spanning tree of weighted graph Q. This is a weighted graph. This is the one example. Q has 6 vertices A, B, C, D, E, F. These are the 6 vertices. And so minimal spanning tree will have 5 edges. 6 vertices, the 5 edges. Each and every edge is weighted. So these are the weighted edges. So from A to C is the 7 weight, A to E 4, A to E 7. Similarly, B to C 8, B to E 7. Like that, these are the each and every edges. It has the 1 weight. First, we order the edges by decreasing according to algorithm 8.2. Order the edges by decreasing weights. Decreasing weights means weight from high value to the low value. Now, within this, highest value is 8. So that is the BC. This is the BC 8. And second highest value is 7. There are 3 sevens. One is the AC and AF. AF and AC. AF and AC. And BE 7. BE 7. And after 7, 6 is there. CE. 6, the next, find the 5. This is BE. After 5, there are 2 4s. One is the AE and DE. AE and DF. AE and DF. The lastly with 3, BD. 3. So this is the arrangement of decreasing weights. Decreasing. So according to algorithm 8.2, just you delete the highest edge and verify whether that is the disconnected, the graph is disconnected or not. So if, for example, if you take the highest value D, BC means this one. If you remove this edge, is it a disconnected graph? No. So that's why you remove. The delete is yes, you delete this particular edge. And the next value is AF, decreasing. AF, this is AF, A and F. Again, you remove this one. And second edge is this one. Again, you remove this one. AF. So you can remove this one because this is not disconnected. Still the edge is there. So that's why this is not disconnected. So if you remove BC, that is not disconnected. If you remove AF, that is also not disconnected. And then third one is the AC. AC is this one. AC is this one. You remove this one. So even if you remove this one also, that is not disconnected because the C can be connected to this one. This edge is there. And A is also connected to this one. This edge is also there because you removed this one and this one. These two removed. Third one is this one. So still we have this edge and the remaining edges. So remove BC, that is S, and AF, this is also S, AC, that is S. Remove these 3. 1, 2, 3. Even though that is not disconnected. Now, for example, if you remove BE, if you remove this BE, so this is the one graph and this is the one graph. That can be disconnected because you already removed this edge. This edge also removed. And if you remove this one, that graph can be disconnected. So that's why don't remove this particular edge. You consider it. BE, you consider the BE. So BE is, delete is no. And CE, for example, if you remove this CE, so you already removed this AC and BC also removed. If you already removed these two. If you also remove this one, the C can be isolated vertex. That may be disconnected. So that's why don't remove this one. CE. So that's why the delete is N. And if you remove BF, B and F. If you remove this B and F, that is a still connected graph. There is no disconnected graph, right? And if you remove AE means A and E. If you remove AE, so that is the no. Means you already removed this one. Don't remove this. If you remove this also, the A may be isolated. The graph is disconnected. So that's why you consider AE. AE is no. How many edges still we have? 3. 1, 2, 3. One is the BE. If you remove this, that is disconnected. So that's why you connected this one, BE. and second one is CE, and third one is AE, right? So still AE, still DF. Suppose if you remove this DF, so whether DF is AE is there, if you remove this DF, you already removed A and F is removed, AF is removed, and BF also removed, BF is removed, AF is removed. If you remove this also, then F is isolated, that may be disconnected. So that's why don't remove this DF, don't remove this DF, you consider the DF. And finally BD. So BD, for example, if you remove this BD, then how many edges here? Only one single edge you consider it. Otherwise, if you remove this BD, this is a D is connected here. So, and you already removed BC, you removed BE, you are not removed this one. BE is there. So DE, DF is there, but there is no connectivity between this and this. That may be disconnected if you remove the B and D. If you remove this B and D, so all these four is a one graph, and D and F is a one more graph, that may be disconnected. So that's why you consider the BD, that is a connected. So all these no means don't delete, yes means delete. So finally, how many N's? No, 1, 2, 3, 4, 5. Total 6 vertices, 5 edges you consider it. From these 5 edges, these are the 5 edges. So the minimal spanning tree of Q contains the edges BE and CE, AE, DF and BD. So with weight is 24. 6 plus 4 is 10. 7 plus 3 is 10. 20 plus 4, 24. So this one is the minimal spanning tree of this one. This is according to the algorithm 8.2. Implement the Kruskal's algorithm. This is the Kruskal's algorithm. This is a different algorithm. So in the Kruskal's algorithm, again you have to find the minimal spanning tree of weighted graph Q. This is the same example. This is the one graph. So you can find the minimal spanning tree. This is the different spanning tree, right? So this is the different spanning tree. Now different minimal spanning tree, but the same weight is 24, because with the same weight multiple edges are there. So that's why different minimal spanning trees may occur, because the edges weights are same with multiple edges, same weight with multiple edges existed. What is the algorithm explains in this Kruskal algorithm? Just you can order all edges in increasing order. Increasing order means low to high. So first we order the edges by increasing weights. Then we successfully add. Instead of deleting, we add. First you increasing order and add. You consider whether the BD, you consider the BD or DF or like that. So whether you add this edge or not, that is decided. That decides. So like that, the edges order increasing weights. The first we order the edges by increasing weights, and then successfully add edges without forming any cycles. If you add one edge, if it forms a cycle, then don't add. If there is no cycle, you consider, you add it. So that process will continue until the 5 edges are included, because total vertices are 6, right? N minus 1 edges, N minus 1. So this yields the data order. This is the 8 BC, that is the B and increasing order BD. BD is the low number, BD, and 4 is the DF. DF, this is the 4, and another 4 is AE, another 4 is AE, and BF is a 5, like that. The final one is BC. This is the arrangement. So now you decide whether you add this particular BD or not. So first 3 weight, least weight value is 3 BD. So you consider this BD. Only this BD, there is no cycle. And DF also you consider it. DF means this one. So 1 and this. This is not cycle. 1 and this. This is not cycle. And AE. AE is here. This is. AE is here. Again there is no cycle. Up to now 1, 2 and this edge. Right? AE. Suppose BF. Where is BF? B and F. If you consider the edge B to F, there is a cycle. There is a cycle. So that's why don't consider it. Don't add. N means, N value is no means don't add. CE. CE. Where is CE? CE. CE. If you add this CE, there is no cycle. So consider it. CE. BE. BE means B and E. B and E. If you add like this, B and E, then there is a cycle. So from E to A to F, A to F to D, D to B. That is a cycle. So that's why don't consider the B and E. That value is no. A and C, AC, AC. If you add AC, again this is the one cycle. Don't consider, don't add. AF, A and F, A and F, this one. A and F, this is the A and F. So this is A and F, this one. A and F is this one. A and F is this one. If you add this one, there is no cycle. So simply you consider it. BC, B and C. If you consider this, that may form the cycle. So that's why don't consider the BC value. So what are the edges you are considering? BD, DF, AE and CE, AF. See this, BD and DF, AE and CAE, after that CE, after that AF. So these are there. Now sum all those things. Minimal spanning tree. This is the minimal spanning tree, contains the edges BD, AE, DF, CE, AF with weight. 6 plus 4 is 10, 10 plus 17, 21, 24. The same with different edges. This is the different. This is the minimal spanning tree with the weight is 24. This is the spanning tree, minimal spanning tree with the weight 24. So both gives the same weight, but the two different minimal spanning trees. Both are the same. Weightage is 24. This is about the Kruskal's algorithm, right? Thank you. Thank you, one and all.